Math 2415, Calculus 3, Section 13.5, Curl and Divergence. Last time we met, we wrapped up Chapter 13, Section 4 about Green's theorem, which gave a pretty strong relationship between a line integral around a closed curve and a double integral over the region bounded by that closed curve. And at the end of this section, we will draw a connection between curl and divergence and Green's theorem. But before we get there, we have to define what curl and divergence are. This first video might be a little lengthy compared to the ones that follow, because not only am I going to define what the curl of a vector field is, but I'm going to explain why it's called curl. The curl of a vector field is essentially a vector associated with rotations around an axis. So think of having say a body of fluid that's rotating around an axis, or a force field where the forces are pushing things around an axis. But how do we calculate this? Well, the first thing you should notice is that a curl of a vector field is a vector field. In other words, curl says give me a point in space. I guess we could talk about it in 2 dimensions by knocking it down a notch. But give me a point in space and I give you a vector associated with it. So it's a vector field. But how do we define it? Well, I'm going to do this a little bit backwards from the way it was historically developed. I'm going to go ahead and give you the traditional definition of curl and then backtrack and show you why it has to do with rotations around an axis. But let's let F be a vector field PQR. And remember, what that means is that the P, the Q, and the R are all functions of x, y, and z. So give me the coordinates of a point in space, and I'll calculate a vector. You can think of the vector originating from that point in space. Then the curl of F is defined as the following vector field. The first component is partial of r with respect to y minus partial of q with respect to z. The second component is the partial of p with respect to z minus the partial of r with respect to x. And the third component is the partial of q with respect to x minus the partial of p with respect to y. You may recognize this third component as the integrand for the double integral in Green's theorem. That's a mess to just memorize. The traditional gimmick for remembering the definition of curl is to define what looks like a vector, but it's not. Well, it sort of is. This is usually called the Dell Operator, short for delta. Excuse me. It's the same symbol we used when we talked about the gradient of a vector field, where we took the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z, if it was an R3, on each component in the vector field. The Dell operator is kind of defined the same way, except it's absent what you're taking the derivatives of. So we're going to define the Dell vector, the Dell operator, as a vector whose components are take the partial with respect to x, take the partial with respect to y, take the partial with respect to z, without saying what you're taking the partial of. So it's almost like a vector of operators, if you will. But if you can get past the fact that these components aren't your standard types of components, they're not functions or numbers, but rather operations or operators that tell you to do something, then we can define the curl of a vector field as the Dell vector cross the vector field F. And we'll demonstrate that in a moment. But I want to show you what this definition actually has to do with describing the rotation around an axis. So I have a scenario set up here. The axis we're going to rotate around is the vector W, which is just going to be some scalar multiple of k. K being the vector 0, 0, 1, 1 in the z direction. So you don't see the z-axis because it's completely covered with the vector W. Now, what is the omega? Well, we'll describe that in a minute, but let me describe the rest of this. Around the W vector, the z-axis if you will, we have a circle representing motion going in a counterclockwise direction. Now, we could probably do it clockwise, but we'll just go counterclockwise for this. If we pick a point on that circle and call its distance from the axis of rotation d. Call the point P, and it stands to reason that if it's going in a circular motion, that its velocity vector is going to be orthogonal to the vector connecting the point on the axis of rotation to P. I didn't actually give that a name, but I guess we could. If we called this point over here, we'll just call it A for the lack of having a name. And we're basically saying that AP, the vector from A to P, is orthogonal to vector V. Makes sense, it's tangent vector on a circle. But how are we going to show that this vector, W, going straight up through the middle of that rotational body, has anything to do with this vector V describing the point going around the circle? Well, the way we're going to do that is we're going to set up a position vector R, whose coordinates are simply x, y, and z. So those are the coordinates of the point P that's rotating around the circle. We're also going to measure a tilt angle from the z-axis to position vector R, and we'll call that angle theta. And for convenience, I went ahead and projected point P down onto the xy plane, and the coordinates of that point, of course, would be x, y, 0. So how are we going to connect this vector over here with the vector around which the body is rotating? Well, one quick comment about the omega. I'm sorry, I didn't tell you that this was an omega. Omega kind of looks like a Greek letter W. I'm going to be very careful to draw my W's pointy and my omegas curvy. The omega, as some of you may know from physics and engineering, omega is a pretty common variable to represent angular velocity, meaning that the angle that the point is rotating around the axis has the same speed regardless of whether it's close to the axis of rotation or further away. Now the linear velocity would be different. The further away you are, the faster you're going linearly, but angularly everybody's rotating the same speed. Now what does that have to do with anything? Well, there's a few ways to define angular velocity. One way to define angular velocity is that the magnitude of the velocity vector, the ratio of the magnitude of the velocity vector to the distance from the axis of rotation is constant. So we can say that our angular velocity is the magnitude of V divided by D. So we're going to take advantage of that. Now, what else can we take advantage of? Well, I'll kind of let you in on the direction I'm heading. To show the relationship between the axis of rotation, which is being represented by vector W, and the vector pointing in the direction of the motion of the point rotating around that axis, I'm going to break this down into 3 steps. Step 1 is I'm going to show that V is the cross product of vector W and vector R. In other words, that the velocity vector for this point going around the axis of rotation is the cross product of the axis of rotation and the position vector associated with the point. Now, how are we going to do this? Well, the first thing I want to point out is that V is orthogonal to the plane containing the the green W and the red R. The fact that it's orthogonal to the R should be evident by the fact that it's perpendicular to the D. And again, it's really kind of hard to see without pulling this. Actually, I can pull this. If we do a top-down view of this picture, then vector V will look something like this. Here's the D measuring the distance from the axis, but the R vector is starting at the origin and ending here. So it's covered by the D, but it's coming straight up. So it should be pretty evident that from the top-down perspective, this is the projection, this vector here is the projection of R onto the XY plane. So we know that V is orthogonal to R. The fact that it's orthogonal to the axis of rotation should also be pretty obvious because the axis of rotation is sticking out here. And if I just translate this vector V across D and put it here, it should be pretty well here. There, it's orthogonal to the axis of rotation, W. So we know that V is orthogonal to W and R. Now that doesn't make it the cross product but it makes it parallel to the cross product, because remember, the cross product is a vector that is orthogonal to two given vectors. And V is also orthogonal to the two given vectors. So since V is orthogonal to both, then we know that V is going to be some scalar multiple, we'll call it C, of W cross R. Now, to show that V is equal to W cross R, we have to show that C is 1. First, let's make note that C is positive by the right-hand rule. If I were to wrap my right hand around to my fingers hitting the W and then the R, then my thumb would be pointing, well, it's easier to see here. The W is here, the R is over here. If I wrap around, I'd be pointing upwards, and that would be the positive value of the cross product. So we already know that C is positive by the right-hand rule. Let's make a note of that. C is greater than 0 by the right-hand rule, RHR. Now, how are we going to get C is equal to 1? Well, to get C is equal to 1, we got to do a little bit more analysis. Let's start with the fact that omega, the angular rotation of this body, is equal to the magnitude of the velocity vector divided by the distance from the axis of rotation, which we've already written over there, right here. What else can we take advantage of? Well, we also know if we were to pull this right triangle out, this one formed by A, the origin, and P. So imagine me pulling that right triangle out. A is up here, the origin is down here, P is over here, and then we have D going across here. Our theta, not all of them, just caps off. Our theta is right here. We know that, what else do we know? We know that, let's see, well, we know that this red vector from O to P represents vector R, so its magnitude is the length of vector OP. And if we form the sine of theta, then we can say sine of theta equals D over the magnitude of R. Sine of theta is equal to D over the magnitude of R. Well, we can fuse these two things together and eliminate the D. So both of these together imply that omega is equal to the magnitude of V times D. But if we solve the second equation for D, it says magnitude of R times sine theta. So magnitude of V, magnitude of, something's a little fishy here. I got my notes on the sideboard over there. What's going on here? This equation's wrong. Oh, that's what's wrong. Omega is not equal to the magnitude of V times the magnitude of D. But the magnitude of V, if we were to solve this for magnitude of V, is omega times D. But D, if we solve this equation, is magnitude of R times sine of theta. So magnitude of D, omega, magnitude of R, sine of theta. But what is omega? Besides the angular velocity, it's also the magnitude of vector W. Should be pretty transparent, because if I take the magnitude of this, omega being positive, we can factor out, and the magnitude of K is 1 because it's a unit vector. So omega is the magnitude of W. We have magnitude of W times magnitude of R times the sine of theta, but that's precisely the magnitude of W cross R. It's the magnitude of the cross product. So here's what we know. The magnitude of V is equal to the magnitude of the cross product of W times R. But we also know the magnitude of V is equal to the magnitude of C times the cross product. C is positive, so we can factor it out. Any scalar you can factor out of a cross product as long as you take its absolute value. But since it's positive, we don't have to take its absolute value. And we have that the magnitude of V is equal to C times the magnitude of W cross R. That's an R there, it looks like an F. Well, the only way these two can be equal to each other, because they both equal the magnitude of V, this implies that C is equal to 1. If you put these equal to each other and divide by the magnitude of the cross product, assuming it's not 0 and it's not, then you get C is equal to 1. So the conclusion we can draw is that V is equal to W cross R. So So this velocity vector isn't just parallel to the cross product, it is the cross product. Well, that's pretty handy. So that was step one. Let's show that V is the velocity vector is the cross product of the axis of rotation vector and the position vector. Step two. Now that we know that V is the cross product of W and R, we're going to find an explicit formula for V. Because we know that W is just omega times K. Well, K is 0, 0, 1. So W is 0, 0, omega. Cross. Our vector R is just X, Y, Z. And we can find this cross product pretty easily by simply putting the second vector in the cross product underneath the first and thinking about our 2 by 2 determinants. For the first component, we cover up the first components and find the determinant 0 minus omega y. Remember, that is an omega. So we get negative omega y. For the second component, we cover up the second components and find the determinant, but don't forget there's a negative in front of it. So if we cover up the second component, the determinant is 0 minus omega x, so it's negative omega x, but the second determinant has another negative in front of it. It's the negative of negative omega x, so it's omega x. And when we find the third component, we would cover up the third components and find the determinant, but it's going to be 0. All right, now we have an explicit formula for the components of the velocity vector. It's going to be negative omega, the rotational, the angular velocity, times y, the y component of this point, and the second component is omega times x, with the third component of 0. It makes sense that the third component is 0. One thing I neglected to mention, my apologies, but I think it's evident from the context. This circle, that point P is rotating around, that circle is parallel to the xy plane. Okay, so we got step 2. Now, where the heck are we going with this? Well, let's calculate the curl of V. And to calculate the curl of V, we can do del cross V. Well, del, as a vector, is partial with respect to x, partial with respect to y, partial with respect to z, cross. And now we have component form for vector V. It's negative omega y, comma omega x, comma 0. And to find that cross product, we can put these second vector's components underneath the first vector's components. And when we form the cross product, we're not really multiplying, we're taking partial derivatives. So, let's see what they are. All right, to find the first component, cover the first components and find the quote-unquote determinant, which is really finding partial derivatives. Partial of 0 with respect to y is 0. Partial of omega x with respect to z is also 0. 0 minus 0 is 0. For the second component, we'll cover up the second components, find the determinant, and take its opposite because of the negative. Remember, we're taking partial derivatives. So, I'll put this back up in a second. Partial of 0 with respect to x is 0, minus partial of negative omega y with respect to z, but that's also 0. 0 minus 0 is 0, and the opposite of 0 is 0. Now let's put these back. Partial y and then omega x. And for the third component, the cross product, cover up the third components, take the determinant. Remember, the determinant here is taking partial derivatives, not products. So along the main diagonal, the partial derivative of omega x with respect to x is omega, minus, in the other diagonal, the partial derivative with respect to y of negative omega y is negative omega. And so we get 0, 0, 2 omega. So what does that tell us? That tells us that the magnitude of the velocity vector is 2 omegas. So vector W tells us two things: the axis of rotation and the velocity at which a point is traveling. Now, one thing that kind of strikes me as odd, and maybe I'm just missing something here. I'm sorry, that's not the magnitude of V, that's the magnitude of the curl of V. Sorry. The magnitude of V is omega times the square root of x squared plus y squared. But the magnitude of the curl is 2 omega. So what that tells you is that this vector, the axis of rotation, tells us two things. Number one, it's the axis of rotation. Number two, twice its magnitude is the angular velocity of the points going around the axis, or vice versa, half the magnitude of the curl represents the angular velocity. So an intimate relation between the axis of rotation and its magnitude relative to angular velocity. I know that was a lot to swallow, and I'll be honest, this is the first time in 20 years of teaching Calculus 3 that I've actually explained up front why curl is called the curl. Actually using it is not nearly as bad until you get to upper level engineering and physics classes, in which case, have fun with that.